Hello. So, covalent bonding. In this lecture, we will consider covalent bonding and its mathematical model. So, the covalent bonding is the interaction between nearest neighbor atom, and this is very important in the covalent bonding. And we consider diatomic molecule, which is a simple model of covalent bonding. Uh, so, A atom and B atom. This is electron. So the distance is Ra and this is Rb, and interatomic internucleus distance is R. And then charge on A at a nucleus is ZaE and B is ZBe, and on electron is minus A. And this is the wave function of this one. This is the nucleus, and this is the nucleus of B. And this is this one. It is this, and this is amplitude, and this is the separation. This is continuous is bonding, and this one is it is anti-bonding, and this is the energy. And this energy, and this one is a bonding, and this is anti-bonding. Bonding has the lowest energy, so lower energy, and this is higher energy. So if you take the Hamiltonian of this function, Hamiltonian is the sum of the kinetic energy and potential energy. Potential energy is the Coulomb interaction. So H is equal to minus h cut squared 2m over del square, or Laplacian. So which is equal to the Coulomb of A and Coulomb potential of B and Coulomb potential because of the nucleus. So the molecular orbital of this wave function is psi mo, and which is the free electron. And solution of the Schrodinger equation is H psi is equal to E energy into psi mo. So the ground state energy, which is will be probability, we will find from this one. So psi star into H into psi into dr over psi star psi into integral of the dr. Psi is equal to the linear combination of states of two separate atoms. So psi A, psi B. So this is S and H A. We will represent this one, and this is H A B. So this is the simple notations. So if we substituted this value, so this one, so we will get this this improve equation of this one, which is this is the coefficient HHA CB squared HBB and 2CACB, which is the coefficient HHAB, and similarly on this one, so CA squared plus CB squared plus 2CACB into S. And the condition of minimum energy, minimum is this one is the gradient of E energy with respect to Ca, and the gradient of energy into with respect to Cb is equal to 0. These conditions will give us two equations, which is equal to Ca into HAA minus E and Cb into HAB. Into ES is equal to 0, and then similarly another one it will be AA, which is AB, which is this one. So AB into ES plus CA, which is HBB minus E. So eliminating CA, so we will get this answer. So HA minus E, HBB minus E, HAB minus ES is equal to 0. So identical nucleus. So if there are two identical nucleus like O2 or H2, so A is equal to B, H is equal to hydrogen atom, HA is equal to HBB. So now two new molecular orbital will have energy which is equal to E plus minus HAA, which is simplified from the equation number 4. So that is the Hamiltonian HAA plus minus HAB plus 1 plus minus S. So there are two conditions. S is equal to 0, two nucleus infinitely large, infinite distance, and S is equal to 1, which is nucleus is uh, coincide the nuclear position. So two nuclei nuclear position coincides. So the equation 7, the spatial overlap of the wave function psi a psi b leads the space splitting of energy level. So HAA HBB into higher and lower energies. So molecular energy. So molecular orbit correspond to higher energy is anti-bonding. So lower energy is the bonding. So reduction in the binding energy, the covalent bonding. So binding energy will be reduced because of this perturbation. So the binding molecular orbital contain only two electron, Pauli exclusion principle, two opposite spins. No two uh, electron can occupy the same space, though they have to have different spin quantum number. Further, electron would have to occupy higher laying antibonding orbitals. So the diatomic molecule bonding orbital additive combination psi a psi b. So the molecule will have this one psi a psi b, and the coefficient will be the same. And if it is a different psi a minus psi b antibonding, so this bonding and antibonding, this will increase in electronic charge density and decrease in charge density. So this will the separation overlap of the wave function. So this is responsible for the bonding. So that determine the gain energy of the bonding orbital of the molecule and the binding energy. So the same orientation overlap of SPD, etc., atomic orbitals. So this is a favorable overlap, and other combinations are not favorable. Only SPD. So strong directional character, covalent bonding in a crystal. So is a like diamond, silicon, and germanium, or uh, uh, diamond, graphite, and graphene. So this is a tetrahedral condition coordination. So diamond is a configuration is 1s2, 2s2, 2p4, 2, and these two will orbital will be the will involve in the covalent bonding. Two covalent bonds, so two 2p orbitals, each one each have contribute to one electron. So 2s orbital electron excited to the 2p orbital. So each have a 2p orbital, 2s orbital. So each of these which participate in the covalent bonding, this is sp3 hybridization. So wave function of nearest neighbor, so overlap, that will be maximum new four new wave function will be formed. Linear combination of a 2s, 2px, 2py, and 2pz. So this will be the so new molecular orbital. So this is sp3 hybridization. This is creation of sp3 tetrahedral hybridization. The gain in energy produced by the overlap, this is a tetrahedral configuration, is more than enough to compensate the energy needed to promote a 2s electron into 2p orbital. So sp3 hybridization will result in tetrahedral geometry, where sp2 will be will be sp2 is a planar hybridization. So 2s plus a 2p, and that is spherical Fullerens C60 structure into many pentagons. So these are topological structure with 12 pentagons. C60 20 hexagon, and sp2 boron. So this one. So binding energy will vary in the covalent bonding. Say diamond, which is a 7.3 electron volt per per atom, and silicon is a 4.64 electron volt per atom, and germanium is 3.87 electron volt per atom. So this is high covalent bonding, and that's why the diamond have the highest uh, hardness. So because of the strong bonding. So this is a covalent bonding.